Okay, and with that, let's switch gears to the next topic of high voltage transmission systems. And our speaker today will be Jiaxiong. Jiaxiong received his bachelor degree from Tsinghua University in electrical engineering, and he's currently working towards his PhD with Dr. Richard Zhang at CPES. His research interests include high voltage DC control and protection, modular multi-level converter, and DC circuit breaker. And the talk that he'll be delivering today is a multifunctional intelligent MMC-based HVDC converter. Floor is yours.
Thank you for your introduction. Hello, everyone. My name is Jiaxiong, and today's topic is about multifunctional intelligent MMC-based HVDC converter. So the outline is background introduction followed by the explanation of principle of intelligent converter and the multifunction explanation, including the online impedance measurements and active damping and assistance to fault current suppression. Then we will go to the conclusion and future work. So let's start with a review of the state-of-the-art power converters nowadays, including the low voltage, medium voltage, and high voltage. Including in low voltage, we have power converters to bring energy from the offshore wind turbine or the solar panels. And with medium voltage, we have 3-level or 5-level motor drives. And in high voltage, we have modular multi-level converter, MMC. So the point here is when we are dealing with higher and higher voltage, the switching frequency of individual power semiconductor devices is actually getting lower from around 10 kilohertz or tens of kilohertz to around 1 kilohertz to like in finally HV high voltage system, we have 100 hertz or 200 hertz switching frequency for individual power semiconductor devices. And the point here is the control bandwidth of the power converters is actually dictated by the switching frequency. So with lower switching frequency, we can only get lower control bandwidth. So the challenges that we are talking about during the previous few days includes the power electronics converters in the power systems. And the dilemma here is how we design or we design the power electronics converters is not consistent with the power system we are dealing with today, meaning that the power electronics converters are designed as a black box with specified terminal behaviors and requirements. So it deals with the fully controllable source and well-defined load with no consideration of interactions with other parts of the system. However, the current and the trends power system we're trying to deal with today is actually a changing system. It is constantly changing source and the load. And with the penetration of the inverter-based resources, IBRs, with high frequency dynamics brings us the challenges to deal with high frequency harmonics. So this is the problems we want to deal with. However, back to 1990s, there were already some research efforts to try to utilize the high control bandwidth of the VSC converters to deal with the system stability issues. So here gives 2 examples. The upper one is an active damping of LC filter proposed by Dr. Vladimir Blasko in 1997. It is done by directly modifying the control loop without requiring additional devices. The lower one is a load conditioner proposed by my advisor, Dr. Richard Zhang, in 1998. So here, an additional device is needed showing in the picture as the load conditioner. So this is on higher switching frequency but lower power rating device that can help shaping the load impedance. So both the upper one and lower one can sufficiently damp the system as shown in the body plot. So back to the challenges we are trying to deal with today, it is actually more severe and more critical than the challenges we are facing like back to 20 years ago. because the penetration and of the renewable energy, including the wind and solar and more demanding and keep changing load like data centers, we are dealing with more severe stability issues, including the subsynchronous and the high frequency harmonic resonance in the power systems. Those are all reported already. So important concept, the intelligent converter concept is proposed here. The detailed explanation or the more detailed explanation includes the rapid detection, the situational awareness, and the adaptive response. So these three concepts is actually one step and one step and one step forward. So the rapid detection is actually enabled by the converter's advanced sensing skills and the ability to kind of, for example, perturb the system to do a system ID. And with the information gathered, the intelligent converter can reach a situational awareness, meaning that it can be aware of the power system where it is located. It can tell that how stable, for example, how stable the power system is by, for example, impedance-based stability analysis. And with all the information and all the intelligence added, it can perform the adaptive response. For example, it can dynamically adjust the control parameters of the VSC, or simultaneously, it can perform the active damping to prevent the small disturbances to grow into a large harmonic resonance in the system. So this page talks about the challenges in high voltage DC system and why we choose this system to demonstrate the idea of intelligent converter. So the unique challenges in HVDC system is actually it's both mission critical and it's a rapidly growing market. However, we are facing the challenges like a limited control bandwidth and much higher insulation requirements. So MMC, or modular multi-level converter, is the de facto choice of the recent developed HVDC project. And right now we are using the silicon-based IGBT device as the power semiconductor devices in MMC. So it's lower cost and with lower switching frequency. And however, if we want to push the control bandwidth, so we have to utilize we have to push our switching frequency. And natural thinking is to use the silicon carbide MOSFET and to balance the cost and the performance. The idea right here is to replace a portion, for example, 5 to 10% of the silicon-based IGBT half-bridge submodules with silicon carbide MOSFET-based full-bridge submodules, as shown in the right-hand side as the blue box. With this modification, it enables the MMC to perform have a higher switching frequency and to push the control bandwidth even further. So before we dive into the different functionalities or the concept of intelligent converters realization, I would like to use this page to introduce the equivalent circuit of MMC and the unique injection methods enabled by the unique topology of MMC. So on the left-hand side is the topology of MMC and the equivalent circuit. So each valve can be regarded as a controlled voltage source if we assume that the capacitor voltage are well balanced. And keep that in mind, the silicon-based full-bridge valve submodules can also be regarded as a control voltage source, as shown in the center side as the blue control voltage source. So there are two injection methods. The left-hand side here, right? Let me use the laser point. Yeah. So if we use the differential mode injection, meaning that if we inject voltage at the 180-degree phase shift, then this in the equivalent circuit, it is equivalent to put a controlled voltage source in the point of common coupling of AC side. However, if we inject voltage at the same phase, then this is equivalent to injection in the DC side. So we can perform the AC side injection and DC side injection. And you will see the importance of this point when we are talking about the impedance measurement. So one page to really briefly introduce the idea of impedance-based stability analysis. So it starts from the Nyquist stability criterion, trying to examine the closed loop system stability with open loop transfer function. If we take a step forward, we divide the system as the grid and the grid type converter, and we write the transfer function from current to voltage like this. We can see that the system stability is actually determined by the denominator of this formula is 1 plus the impedance of the grid times the admittance of the grid type converter. So this is essentially so this term is called the return ratio, and this of interest of us. And if we want to study the stability of the AC system, then we have to use the generalized Nyquist criteria. It's a generalization from a single input, single output system to a multi-input, multi-output system. So the expression turns into ZG times YC, where they are 2 times 2 matrix instead of a single complex value. And it can be performed in either the DQ rotating frame or the sequence domain for whatever you choose. Another page to just give you a very brief idea why we kind of prefer the frequency domain analysis, or why the time domain simulation may not be sufficient. You can see from the simulation right here that even the small, very small system disturbances can, if it is given a sufficient amount of time, it can sometimes grow into a large harmonics disturbance, harmonics resonance, and it can finally destroy your system. So we need this analytical method to ensure system stability. So another page to introduce the previous CPES work as the impedance measurement units. So this is the implementation in either low voltage or medium voltage can perform the shunt and series injection. You can imagine that, and as you can see, when we move into the medium voltage range, the impedance measurement unit is already big enough. So if there exists a dedicated device in high voltage, then the size of it is comparable to that of real HVDC converter like MMC. So this is not really affordable. So the proposed method here is trying to, without a dedicated device, but still using the impedance measurement method to tell the system stability. So this is really a page to show the system on the research, and the left-hand side is the reference project at SOO Green HVDC link with plus minus 525 kV as the system DC voltage and 350 miles as the underground cable. And the right-hand side shows that the simulation was performed in Plex software and is a submodule level switch model. So this page is giving you a basic idea about how to perform the impedance measurement using the equivalent circuit mentioned previously. So if you still remember, if we are using the differential mode injection, this is equivalent to putting a voltage source at the AC common coupling, point of common coupling, then this is essentially a voltage perturbation injection. So there is no need to use dedicated device to inject perturbation in this case. And right-hand side is to tell you how is the basic steps to perform the impedance measurement. And this page is showing the simulation results. The left-hand side is one injection in time domain, and the right-hand side is both the DC side result and the AC side, or both the grid side and converter side body plot of the system impedance. So those body plot or Nyquist plot of the converter or the grid impedance are used to examine the system stability afterwards. So starting from this page, we're trying to deal with the existing harmonics resonance in the system. So the harmonics resonance in the system is mainly caused by the impedance interaction between the converter itself and the AC grid. And since the AC grid is keep changing and you really don't have a a complete idea about how it is composed, then sometimes it appears to be that the resonance comes from nowhere. So the waveform right here is actually showing the fifth order harmonics and seventh order harmonics is the dominant harmonics component in the system. However, in the real world system, this might not be the case because the harmonics resonance can be a few hundred hertz or even higher to, for example, around 1 kilohertz. So if the resonant frequency goes beyond the control bandwidth, how to deal with it? So we can also perform the active damping using the injection method that was introduced previously. So the active damping is really to try to shape the impedance of either the grid-tied inverter or the grid. And the concept or the control flowchart is shown like here. We first sense the current in the PCC point go through a high pass filter and times the R damp, which is the virtual resistance we want to add at the point of common coupling. So with this method, this is equivalent to add those virtual resistance only be seen by the high frequency components of the current. So the simulation result in this page shows that once the active damping is enabled, the fifth order and the seventh order harmonics of this of the current is sufficiently damped. And to be mentioned that this is only a demonstration of the ability to actually damp the system's harmonics, and this is not limited to damp the fifth and seventh order harmonics, and the frequency is actually limited by the switching frequency of those silicon carbide MOSFET. So a benefit of this is the damping resistance is virtual resistance in high frequency range. Thus, it doesn't have those loss of the like the passive damping, and the damping resistance can be adjusted dynamically. So this page, we finally talks about the protection in HVDC transmission system and how our multifunctional intelligent HVDC converter is going to deal with it. So with this symmetrical monopole system, when we have a hub bridge MMC configuration, we can either use the AC side circuit breaker or the DC circuit breaker, which is pretty expensive. And if we choose to use the full bridge converter, full bridge MMC or a hybrid MMC with at least 50% full bridge, we can use those full bridges to block the fault and to prevent the current to flow from the AC side to the DC when there is fault in the DC side. So this gives us an idea that the percentage of the full bridges in the MMC is actually the ability of how well you can block the DC fault. So this is really remains to be a design choice. If you want this converter to have a higher DC fault blocking capability, you choose a higher percentage. If you don't mind or you have other system other protection methods, you can kind of limit the percentage to like 5 to 10%. Anyway, as you can see from the simulation results, although it cannot fully block the DC fault, it can decrease the rate of rise of the fault current at the very early stage of the fault. Then it can earn some time for the other system protection mechanisms to react. So this is the third and the last functionality of the proposed multifunctional converter. So this page is showing the ongoing work, which is the hardware prototype that happens in the Arlington lab of CPES. So we have the OPRT as the HVDC converter, and we have almost 200 full bridges as the power switches, and we are designing and testing the control interface to really bring the gating signal to the power switches and to read the current and the voltage signals from the power switches back to the HVDC controller to perform those multi-functions. So we finally reached to the conclusion page, which is we propose a multifunctional intelligent MMC-based HVDC converter, and which can perform the online impedance measurement, active damping, and assistance to fault current suppression. And most importantly, this presentation introduced a very important concept, which is the intelligent converter with the situational awareness, rapid detection, and adaptive response. So here is everything about my presentation. Thank you, and I would be happy to take any questions.
Nice presentation. All right, so let's open the floor for some Q&As.
Thank you for your presentation. This is Ashkan from CPES. Can you go back to your slide, I guess number 13, when you showed the impedance measurement unit and the HVDC from Siemens? Or here you showed the impedance measurement unit that is built out of SiC MOSFETs, and then showed the MMC from Siemens or Hitachi that is made out of IGBTs. I'm not sure if I really got your point here as the motivation of the work. Can you please elaborate on this?
Sure. So this is really about giving you a basic idea how large it would be if you want to develop a impedance measurement unit in high voltage application. So because on the left hand side of the picture, you can see that in medium voltage it is already that big. So you can imagine. So the right hand side is a picture of MMC. You are right. So as you can imagine, that if you want to deal with the high voltage in the HVDC, then it will be really big and it's not really applicable. So that's the point I want to make here.
I see.
Yeah.
All right. Thank you. Yep. Thank you very much.
All right. Thank you all again, and let's thank the speaker again.